Let us discuss now types of functions. Before we proceed to identifying some types of functions, let's emphasize first some important things in dealing with functions and their graphs. First is the x-intercept. What is an x-intercept? The x-intercept is the abscissa of a point where the graph of the function intersects the x-axis. Take note, guys, that in your previous math, in the Cartesian coordinate system or rectangular coordinate system, the ordered pair there is also called coordinate. Okay, this point here is called coordinate, and the x, the value of x is called the abscissa, and the value of y is called the ordinate. Okay, just a quick review on that. So when we say x-intercept, this is the abscissa of a point where the graph of the function intersects the x-axis. Basically, this is the value of x when y is equal to 0. So don't be confused with the subscript I there. This is just the value of x. Of course, it's not everything, it's not all values of x. It's just one value of x in that it happened that that value is the x-intercept. Next is the y-intercept. The y-intercept is the ordinate of a point where the graph of a function crosses the y-axis. Basically, this is simply the value of y when x is equal to 0. That's the ordered pair of y and y sub I. Note that a function can have more than one x-intercept but can never have more than y-intercept. So I'd like to write that one. So take note that a function can have more than one x-intercept but can never have more than one y-intercept. Why is that so? If it has more than one y-intercept, then that is not already a function. Meaning, if we draw that graph and the vertical line, using the vertical line test, and that line intersects more than one point in the graph, then that graph is not a function. So that's the main reason. So if we have, just for the sake of illustrating it, if we have this rectangular coordinate system, this is the x-axis and the y-axis. Suppose we have this point, and assuming this is our graph, this is our f of x. This point here is the value of x when y is 0. So basically that's the x-intercept, and this one here is the value of y when x is 0. So that is 0x and a value of y, and basically that is the y-intercept. So the idea of x and the y-intercept is very important in graphing functions. Okay, it's very important in graphing functions because most functions are graphed starting from the x and the y-intercept, and it is easier if we start from the x and the y-intercept in graphing functions. Now, given the graph of the function, it is easier to identify the domain and the range from a graph. Finding the domain and range from a graph. Okay, Suppose we have this, again, rectangular coordinate system. If this is our A, and this is our B, this is our C, and this is our D. If we have this graph here, okay, if we have this graph here, to find the domain of this function, simply look at the values of x in the y-axis and the x-axis where that function exists. Okay, so in this case, it exists from A to B, and also the range, consider the y-axis, so find the interval where the function exists in the y-axis. So in that case, our range would be from C to D, where C and D are included, because that is a shaded circle. Another example, if we have this A and this is our C, so if we have this kind of function here, assuming that is our function, our D here, again, just consider the x-axis. So the graph exists from A to positive infinity, or just infinity, but A here is not included, so we use the open parenthesis because it is an open circle. Then for the range is from C, again C is not included, to positive infinity. Now let's have another example. Again, this is our rectangular coordinate system. If this is our A, this is our B, this is our C, and this is our D. Suppose we have this kind of graph. Suppose we have this kind of graph. Okay. In this case, our D, our domain of the function, is from negative infinity because of this arrowhead here of the graph. So it goes to the negative infinity to B, but in this case B is not included. Then for our range, it starts from C, and C is included, to positive infinity. So basically, if the graph is given, it would be easier to identify the domain and the range. Again, just consider the x-axis in finding the domain of the graph, and consider the y-axis in finding the range of the graph. Given the intervals from the x-axis, we would know whether the function or a function is increasing, decreasing, and constant in a particular interval. So what are increasing, decreasing, and constant functions? Let I be an interval in the domain of f. Then f is increasing if f of b is greater than f of a whenever b is greater than a in that particular interval. Again, the interval is a subset of the domain of f. Second, f is decreasing on I if f of b is less than f of a whenever b is greater than a in I. So the third one, f is constant if f of a is equal to f of b for all a, b in I. So example, suppose we have this rectangular coordinate system. This is the x, this is the y, this is 1, 2, 3, 4, -1, -2, -3, negative 4. Suppose this is our function. If we take our I would be negative 3 to negative 2, meaning we take this function here from this point to this point. So in that case, obviously from the graph, it is increasing. So f is increasing on negative 3, negative 2. Now if we take I from, let's say, negative 1 to 1, so here, from here to here, assuming that is a line and that is parallel to our x-axis. So what if you substitute, if this is supposedly f of x, and if you substitute in that particular function from negative 1 to 1, the value of f of negative 1 is just equivalent to f of 1. But in that case, you can just check on the graph, assuming that is a straight line parallel to the x-axis. So in that case, f is constant on negative 1, 1. Now if we have, say, 3, I is from 3 to, let's say, positive infinity. So by just looking at the graph, f is decreasing on 3 to positive infinity. Later on our examples of functions, it would be easier for us to identify if a function is increasing, decreasing, or constant on a particular interval. Why? Because you just have to substitute the values of x on the function, then just compare if one value is greater than the other. Okay. Now we are ready to discuss the types of function. First is constant function. A function f is a constant function if f of x is equal to a. Okay. If f of x is equal to a, where a is elements of real numbers. So if we have, let's say, f of x equals 5, so whatever value of x, then the value of y will always be 5. In the graph, if this is our RCS, 5, 1, 2, 3, 4, 5, this is the graph of that function. Okay, f of x is equal to 5. So whatever value of x you substitute in the function, the y will always give, or the function will always give us 5. So that function is a constant function. Next is the linear functions. A function f is a linear function if f of x is equal to mx plus b, where m is not equal to 0, and m and b are real numbers. So the restriction m is not equal to 0 there doesn't mean the function does not exist. It only a restriction that if m is equal to 0, that function is a constant function. Okay. Now there is an emphasis that a linear function, a constant function, is not a linear function, because the graph of a linear function, which is f of x is equal to mx plus b, where m is not equal to 0, is a non-vertical and non-horizontal straight line with slope m and y-intercept b. So again, our m is a slope. As a review from your previous math, when you say slope, it is given by a change in y over a change in x in the graph, or you can write that one as y sub 2 minus y sub 1 over x sub 2 minus x sub 1 if 2 points are given. Or we sometimes call it rise over run, especially when we graph the linear functions. Okay. Now, there are two forms of linear functions. Okay. One is increasing from left to right, and one is decreasing from left to right. The graph is increasing from left to right if the slope is positive, meaning it is increasing on the interval negative infinity to positive infinity. And the graph is decreasing from left to right if m is less than 0 or m is negative. So that is decreasing on negative infinity to positive infinity. Now it is easy to identify the domain of the linear functions. As you can see, it is just increasing from negative infinity to positive infinity. So the domain of this is all real numbers, so as the range of linear functions. All real numbers, the set of all real numbers. So again, if m is equal to 0, then that function is a constant function. It's not a linear function anymore. So let's proceed now in graphing linear function. Example, if we have f of x is equal to negative 2x plus 3. Again, our m here is negative 2, and negative 2 can be written as negative 2 over 1 or 2 over negative 1. Okay, that's the same. And our b here is 3. Again, our b is y-intercept. Again, the y-intercept is just as an ordered pair, which is 0, 3. So graphing this function, you already have an idea that it is decreasing from negative infinity to positive infinity because our slope is negative. So you can start from the y-intercept, which is 3. 1, 2, 3. This point here, which is 0, 3. Then you can use either of the two, either this one or this one. You will still come up with the same line. Okay, so example, we use the first one. Our rise is negative 2, so from the y-intercept we count negative 2 down since it is negative. So 1, 2, then our run is 1. From that point we count 1 to the right. So this one here, that ordered pair there, is 1, which is the value of x, and 1, which is the value of y. Remember, this is 1, 2, 3. Now if you connect the points, this is f of x is equal to negative 2x plus 3. Now you can also, if you don't want to use the y-intercept and the slope, you can just find arbitrary points. Okay, you can just, since the domain is from negative infinity to positive infinity, you can just take any values of x, 2 values of x, then find values of y, then connect those points. Okay, very good.